Lecture 6 covers sections 3.3. At the end of the lecture, you should be able to understand how resistors in a series configuration divide voltage, and also formulate an expression for the voltage across a resistor in series with other resistors. To begin, let us consider the following circuit. Imagine we have a voltage source Vs that's connected to resistor R1 that is connected to resistors R2 and R3 in a series configuration. We want to determine the voltage drop across each resistor. We can begin by constructing a KVL loop and applying our KVL equation, i.e. Kirchhoff's voltage law, to our system. Starting in the bottom left-hand corner, we enter the negative terminal of our voltage source. For there, we proceed to the positive terminal of R1, the positive terminal of R2, and the positive terminal of R3 before returning to our point of origination. Thus, our KVL equation is minus Vs plus V1 plus V2 plus V3 is equal to 0. Or we could write that our source voltage is equal to the summation of our voltage drops across our resistors R1, R2, and R3. Now, to determine the voltage drop across each resistor, we have to apply Ohm's law to solve for each individual V. Recalling the current running through each resistor is the same, we can formulate our KVL equation such that our source voltage is equal to I, our current running through each resistor, times the summation of our resistances. That is, I times the quantity R1 plus R2 plus R3. We can solve for our current via our KVL equation, for which we applied Ohm's law, where our current running through our system is equal to our source voltage per the sum of the resistances of our resistors. Recalling Ohm's law states that the voltage drop across an element is equal to current flowing through it times the resistance, we can formulate this equation to the voltage drop across resistor 1, such that V1 would be equal to our current running through it times our resistance, where we just solved for our current I1, and we multiply that equation by R1, such that V1 is equal to the quantity R1 per the sum of R1 plus R2 plus R3 times our source voltage. We can repeat this process to solve for a voltage drop across resistor 2 and resistor 3 to take the following formulation. V2 is equal to R2 for the quantity R1 plus R2 plus R3, all times our source voltage, and V3 is equal to R3 per the quantity R1 plus R2 plus R3 times our source voltage. So, can we formulate a general expression for the voltage drop across a resistor in series? And the answer is yes. Our generalized expression would be the resistance associated with the voltage drop of interest. And we're going to designate this by the subscript n. Now, this quantity, R sub n, would be per the sum of the resistances in our series configuration. This entire quantity would be multiplied by our source voltage, such that we can say V sub n, or the voltage drop across our resistor n of interest, would be the current flowing through it times the resistance of that resistor. This would be equal to R sub n per the quantity R1 plus R2 all the way up to R sub capital N, where capital N indicates the number of resistors in series. This quantity would be multiplied by our source voltage, and we can express this more simply by saying V sub n would be equal to R sub n per the summation from I is equal to 1 to capital N of R sub I times our source voltage. Now, there's an interesting consequence of this. We can replace the resistors in series as one resistor. We see that in the denominator of our V sub n equation, our resistances sum algebraically. That is, we had R1 plus R2 all the way up to R sub capital N. We call the denominator our equivalent resistance, and we're going to denote this by the variable R sub s, where s indicates a series configuration. Thus, we can express R sub s as a sum from I is equal to 1 to n of R sub I, which was identical to the denominator in our V sub n equation on the previous slide. Now, note this expression is only valid for resistors in a series configuration. To verify that we have the correct formulation, we want to see that our equivalent resistance satisfies the conservation of electrical power and Ohm's law. If we go back to original circuit, we can express the power dissipated by each resistor as the current flowing through it squared times its resistance. That is, our power dissipated would be the power dissipated by resistor 1 plus our power dissipated by resistor 2 plus our power dissipated by resistor 3. Or this is equal to I squared R1 plus I squared R2 plus I squared R3. Now if we recall our expression for equivalent resistance, we can re-express our power dissipated within our system as I squared Rs. These two expressions are equivalent and they satisfy the conservation of electrical power. That is, our resistors are dissipating the same quantity of energy regardless of whether or not we express each individual power dissipated or use our equivalent resistance. To verify that our equivalent resistance satisfies Ohm's law, we'd look at the voltage drop across our resistors in series. That is, looking at our KVL equation, Vs would be equal to V1 plus V2 plus V3, which would be equal to the current flowing through each resistor times their respective resistances, i.e. IR1 plus IR2 plus IR3, which is identically equal to IRS. Thus, our equivalent resistance satisfies the conservation of electrical power and Ohm's law.